The impetus for the DART mission was to answer the question, if an asteroid one day is discovered heading for the Earth, what would you do?
Very, very broadly, we needed to demonstrate that we could intercept a body in space that we had never been to, and that we could change that body's orbit.
Pre-DART, everything was theoretical. There hadn't been any in-flight demonstration of a technology that could potentially prevent an asteroid from hitting the Earth. And it's exciting that we've taken this first step. Earth has been hit by asteroids for billions of years. This has happened in the past, it will happen in the future.
And planetary defense is trying to prevent those impacts from having a bad effect on us here on Earth.
There have been theories about what kind of things we could do at an asteroid if an asteroid was coming towards Earth. However, the most practical one, and the one you have to try at first, is go and hit an asteroid.
The kinetic impactor technique is basically you have an asteroid that's moving in a direction at a speed that is going to take it to intersect the Earth, and you launch a spacecraft and collide it with the asteroid. That changes the asteroid's orbit so that it no longer hits the Earth.
If you do the experiment at a binary system, this is two asteroids, one of which orbits the other, you're able to measure that change using telescopes from the Earth. There's only a very small number of asteroids that you can do this experiment at. Didymos is by far the best.
This made this a very cost-effective way to do this first test, a very focused way to do this first test, taking this from something that was just theory to now a reality.
3, 2, 1. And liftoff of the Falcon 9 and DART.
Dimorphos is by far the smallest object that's ever been targeted by a NASA spacecraft. And we were hitting it at several times the speed of a rifle bullet, 6.5 kilometers per second.
The spacecraft has to do everything itself. Find the asteroid, guide towards it, impact it.
Smart nav, I always considered the brain. So it was making course corrections based on our trajectory to the Didymos system and then finally to Dimorphos.
Ejecta is all of the dust and rocks, and in some cases boulders, thrown off of the asteroid, giving the asteroid an extra push by that material that's getting shot off.
We wanted to observe it, want to know how much there was, how fast it's going, to help us determine how much deflection does a kinetic impactor produce when it hits the target.
The simulations and the theory ahead of time predicted a wide range of results, but without actually doing the experiment, there was a lot of question about how it would work out.
Honestly, the day before impact, I slept strangely well.
We've tested our spacecraft on the ground, we tested our spacecraft in flight. We knew it like the back of our hands.
Hundreds of people across APL contributed to this. Scientists around the world involved, telescopes ready to go to watch the effect. Yeah, I was really happy that the day was finally here and we were going to do this.
And tonight, we're following the real-time journey of the DART spacecraft and its planned collision with asteroid Dimorphos.
One of the big challenges was we cannot even see the target because it's behind the other asteroid until, 1.5 hours before the impact.
We slowly started getting closer and closer in. At 4 hours out, our spacecraft became completely autonomous.
Okay, do we see the second moon? If we don't see it, there's no way the spacecraft's gonna see it.
And we were all huddled around our phones, looking at the team Slack. And once we saw that we could see two Didymos and Dimorphos as separate dots, I said, we're good, we're gonna hit it.
Yes, you start seeing the features on it. It's like, wow, it's got boulders, it's got huge boulders.
It was the most amazing feeling, and even talking about it right now, I'm getting goosebumps.
Are we there yet? Are we there yet? Are we there yet? The last image came in. It was less than a second prior to impact. You could see the red on the camera, and I don't think I've ever cheered for losing a signal with a spacecraft before, but definitely did that time.
I was sitting on the lawn here. Within 2 minutes, people were saying, hey, it's getting brighter in Kenya. Hey, it's getting brighter in South Africa. We think we're seeing this.
We started getting the reports in from the telescopic observations. Oh, we saw. There was an immediate, dramatic brightening of the system.
LICIACube, the Light Italian CubeSat for imaging of asteroids contributed by the Italian Space Agency, it started taking its images and it made its close flyby 3 minutes afterwards. And what you saw is these huge ejecta streamers.
People were trying to measure how much we actually changed the orbit of the asteroid. We were hoping for something like 3 to 10 minutes.
We actually made a period change that was more like a half hour, and we made a lot of ejecta.
It means that you can deflect a larger asteroid than you thought you could before. If you had less warning time, let the asteroid get closer to you before you detect it, you could still be able to make it miss the Earth.
We're learning so much more about the surface properties of the asteroids, the cohesion properties of the asteroids.
If we were to find something, we now have an option, another tool in our toolbox.
We take all of the information that we have learned from DART, and we can now directly apply it for the future planetary defense operations.
It really pushes the capabilities of what we could do on board the spacecraft and what the mission concepts could be in the future. So it's just the beginning.